Hello everybody, today we're going to present the topic Bio-inspired UAV two-blade propeller for the RQ-11 Raven, which will be presented by me, Karen Quevedo, and my teammates Valeria Luna, Shedar Escalante, and Jose Marin. So the agenda for this presentation is going to be the introduction as the first topic, then we're going to continue with design, then market analysis, manufacturing systems, characterizations, and then we will conclude. So let's start with introduction. So the main objective of this project was to make a better design in order to improve a brake propeller. We also focus on the aerodynamics and aeroacoustics performances that we mentioned on the midterm presentation, and then now we focus on the analyzing each aspect of the propeller with different classes and knowledge that we got through all these years, and the main focus was to improve battery life and reduce noise emission. The problem statement of this project focuses on the crucial device that is implemented by the military in missions. This is a surveillance device that should perform at its best because it may bring consequences to the operator by giving away the position or just crashing because of the battery life. So the area of improvement that we found was that the device was really noisy and that the battery did not last long enough. Sometimes the operators just lost the device and it landed anywhere, so that was a problem for them.
Constraints. The constraints faced during the project was the decision of the method for the creation of the blade propeller. At the beginning of the project, the team investigates several methods to develop the bombs. The easiest and first method selected was print the prototype on PLC, but after several research, the team found out that this material will not be resistant enough for the design test, and the surface finish will not be smooth as in resin printing.
Here is the senior design Gantt chart, and this is the date after the midterm presentation. So these are the list of activities that the team was doing, and we completed. We have a start date and a completion date, and then we divided each task by each team member, and you can see like through the line that it has been completed until yesterday, everything. The PER chart, just like the Gantt chart, is the outlined process of the project to maintain all tasks fulfilling each other, so it can be like a following process. This PER chart was updated because of the situation we're living in, and some tasks changed it in order to make a safer way for members of the team. The CPM is also a task tracking for the project, and this helped it to find the critical path. Here's the listed activities. In the following slide, it can be seen that the critical path is listed. Now we're going to present the design chapter.
These are the CAD models that we created by using Autodesk Fusion 360. The parameters for the blades were set by using a method called blade element theory with the assistance of Dr. Shotapalli. The airfoil profile used in all of the blades is an NACA 0012. The model on the left doesn't have any bumps, it's a regular propeller. The model on the center has 4 bumps, and the model on the right has 8 bumps. This is a front view of one of the models. As you can see from the figure on the left, the starting angle of attack at the root of the hub is 53 degrees, and then on the figure on the right, you can see how it starts to straighten out until the tip, and the final angle of attack is 20 degrees. In this slide, you can see an engineering drawing on one of the propellers. We have a top view, a front view, and a right view. On the top view, you can see that the propeller is 14 inches in length. On the front view, you can see a cross-section of the propeller and that the hub is 1.3 inches in thickness, and also there's a new hole that is 0.85 inches in depth of 1 inch in diameter. All of the blades have the same basic measurements with the exception of the bumps. This was the last modification that we applied on the designs. We found out that the hub was way too thick and it would not fit in on the thrust analyzer if we tried to mount it. This is partially because of the starting angle of attack at the root of the hub, and since we didn't want to mess with the geometry of the blade by making the hub shorter, what we did essentially was to make a hole on the top face, and that way we could get access to the base of the thrust analyzer and screw it. For the process analysis, last time we talked about printing the prototypes on PLA, but since then we decided to do it in resin, or at least try to do it in resin, because PLA didn't leave a smooth surface finish, and that would affect on the airflow at the when it impacts the leading edge of the propellers. And also we found out that they aren't as resistant as they need to be, especially because of the high velocities that we were trying to reach. So instead we opted for resin. We also considered using carbon fiber, but we stuck with resin because we thought that it was the best option in this application.
Now we're going to talk about market analysis.
Market analysis. Launching into the market. How our product could compete in the market? Well, today the RQ-11 Raven is the most commonly used UAV. The main difference with the competitors are the weight, proportion, and battery life. Since the soldier usually goes by foot, the RQ-11 Raven is the most accurate device to use. Even when the RQ-20 Puma has a bigger range and long battery life, their weight makes it impractical to manage. And according with the research, the last order of this model was in 2014. An important aspect to mention is that this new design not only grows the battery endurance and reduces noise, since in some cases the soldier using this device in an unknown or dangerous region, in consequence making the RQ-11 Raven capable of return at the point in which it was launched, can not only save it for mechanical or physical damage, it also may save the life of the soldier, and this impacts significantly about how much the customer is willing to pay. The competitors. In this slide, you can observe the two principal competitors of the RQ-11 Raven, and it is possible to observe that the RQ-12 Wasp is lighter than the RQ-11 Raven, but the range and the battery life are lower. Positioning chart. The positioning chart displays the RQ-11 Raven in the middle. With the improvement previously explained by my partners, the RQ-11 Raven will be positioning closer to the RQ-20 Puma in terms of battery durability, without increase the cost significantly. The size of the circle corresponds to the range, which are 5 km for the RQ-12 Wasp, 10 km for the RQ-11 Raven, and 28 km for the RQ-20 Puma. Business model. In this business model, you can observe as one of our key partners the raw material seller, which in this case will be the resin seller, and the original RQ-11 Raven manufacturer. Why? Because our objective is develop the improvement in the blade propeller without changing any other part of the RQ-11 Raven. And as research indicates, this manufacturer buys the blade, he does not manufacture them. In the value proposition are the two objectives of the project: increase the battery life and reduce noise. Our key activities include innovation, since the blade propellers are an existing product. Packaging, because of course we need to send them. For the same reason, the distributor is one of our key partners. The production is our most important activity. Our channel will be website order, since it's the best way to sell in this decade, and the direct email for any question. Risk analysis. The hazard represents what could happen. For example, in the situation of pandemic in which we live today for the COVID-19, even when our market is not affected directly because our principal customers are armed forces, one of our assets on risk could be the operation that may be interrupted.
Now we're going to talk about the manufacturing systems. Product process was the main idea of the whole project. So first we found the problem and the need statement. in order to come up with possible solutions. Then we found the possible improvements and then developed a 3D model. After printing the 3D model, we will develop the test and the launch in the market. In this FMEA, we're focusing on the printing process. Simulating, we already have a proper little manufacturing plan. So the main failure modes were identified along the printing process. For example, having an issue of temperature, and this could make the part go wrong or come up with bad quality, and which then it will need to be printed again, causing some delay, and worst case scenario, the client don't wanting the part anymore and changing to another organization. Another example that could go wrong while using the resin printer could be that the operator could get toxic material into his eyes or mouth, causing a hazardous situation for the employee and the employer.
Characterizations. The UAV is exposed to a challenging environment that will be higher in velocity, temperature, and altitude, and can cause failure. This failure can be solved by performing a thermal and flow analysis of the UAV. Thermal and flow characteristics of the RQ-11 Raven. Provided on the small unnamed aircraft system, RQ-11 Raven technical manual specifies the operational temperatures. The UAV can be operated in winds higher than 20 knots, but with reduced mission capabilities and higher risk of damage during launch, landing, and recovery. The UAV is also capable of resisting a maximum of 0.25 inches per hour of water, except for battery chargers, which should not be operated in rain. The model can resist a temperature range of -29 to 50 degrees Celsius. There are significant challenges to perform a flow-only analysis, such as high velocity and the change in fluid properties due to the altitude. These properties can make vibration, also known as turbulence. Turbulence from the propeller is usually caused by a mass imbalance. A mass imbalance is when the center of gravity of the propeller is not in the same location as the center of rotation of the propeller. Some of the flow limitations found on the technical manual are: the normal operating altitude is from 150 to 1,000 feet above ground level. Operating above 500 feet above ground level can be accomplished but with reduced video sensor performance. Also a range of 10 kilometers and a maximum flight altitude of 10,500 feet. The following are fluid factors of the propeller. For a propeller-powered aircraft, the gas that is accelerated on the working fluid is the surrounding air that passes through the propeller. The air that is used for combustion in the engine provides very little thrust because the blades rotate, the tips move faster than the hub. So to make the propeller efficient, the blades are usually twisted from the hub to the tip. The angle of attack of the airfoils and the tip is lower than at the hub. A closer look at how propellers cause forward thrust will reveal that the hovercraft moves forward by pushing air behind it. To understand this, we turn to a principle that was discovered about 300 years ago, Bernoulli's principle. Anytime that the wind is blowing, pressure of the moving air becomes less than it would be if the air wasn't moving. If you can cause air to move faster on one side of the surface than the other, pressure on that side of the surface will be less than the pressure of the opposite side. Propellers use an atmospheric pressure differential to support aircraft propels forward or upwards. Bernoulli's principle states that the faster moving air has lower air pressure, and higher air pressure is found in slower moving air. As you can see in the image, the propeller has blades that spin in a circular motion. In both cases, lift is generated by the high pressure pushing the wings and blades up. Thrust can help fight the effect of wind resistance, which does translate to some speed. But RPM is an even bigger factor, as it turns out. RPM can be figured out by taking your motor's kV and multiplying it by your battery voltage. The RQ-11 Raven uses an Aveox 27267 electrical motor. It produces 726 kV. It also uses two types of batteries. The first one is a single use and the second one is a rechargeable. The first one reaches an RPM of 2032.8 and the second one 2613.6 RPMs.
To conclude, we're going to give several points on each factor that was taken into account for this design. Public health and safety. Since we're working with resin, there are rules that need to be considered, such as curing the resin faster so that toxic materials don't go into the air and affect the operator. Working in ventilated areas is also important. Welfare. It is important to consider that implementing these changes to the blade will reduce the noise, and the soldiers in the field can be considered to be safer, so they can come home with their families. Cultural factor. Since 3D printing is now all over the world, people are familiar with the process and these are not affected even in being in different cities. These topics are more deeper touched in the final report.
Environmental factors. The aerodynamics noise generated from an operated rotary wing UAV could affect human life as well as wild animals. A research example states that the noise generated from a UAV could significantly increase the heart rate of bears, which indicate an undesirable stress response. Social factors. In combat zone, you don't want to scare the locals because they are the ones that provide you with information. With the bio-inspired design, it reduces noise, giving it a less aggressive look to the Raven. In this way, it prevents communities from feeling emotionally threatened or attacked. Another social factor is that there has not been official place that states that the RQ-11 Raven is operated by men only, but in most occasions it has been used by men in combat units. However, any soldier can be trained or certified to use the Raven. Finally, global factors. The U.S. military uses drones in practically every mission. It is estimated that roughly 30% of their aircraft are drones. The Raven is used by the United States Army, Air Force, Marine Corps, and Special Operations Command. Additionally, foreign customers include Australia, Estonia, Italy, Denmark, and Spain, which are military allies. The Raven is the most widely adopted UAV system in the world today.
As a team, we would like to thank all the professors that guide us in this project. Completed reference will be in final report. Thank you.